Okay, for this problem, we are given that x of t is wide-sense stationary process with the expected value of x of t is n, which is a constant, and the autocorrelation rx of t1 and t1 of t2 of t is equivalent to rx of tau. And we're also given that y of t is equal to x prime of t. So we need to find out what the expected value of y of t is. So from that, we do some plugging and chugging. So the expected value of y of t is equivalent to the expected value of x prime of t. And that is also equivalent to the derivative of n, which was given by it being wide-sense stationary as a constant, which leads the value to be 0. So that's the answer for part A. Part B is the expected value of x of t multiplied by y of t. So x of t is wide-sense stationary again. So we're looking at the autocorrelation of tau, which is equal to r of 0. Now from this, we write this formula, so it's rt of t is equal to the expected value of x of t multiplied by x of t. So if we take the derivative of this, then we get to here, which we take the derivative with respect to t of the expected value of x of t squared. Now if you do that, you get 2 times the expected value of x of t times x prime of t. And if we remember, the x prime of t is equivalent to y of t, so we can substitute that in. Now from that, we are given that this is the expected value of 0 from what we found out up here. So the answer is 0. So to figure out if it is uncorrelated, you have to show what we proved up here previously, which the expected value of x of t multiplied by y of t is equal to 0. And we see that the expected value of t times the expected value of y of t is equal to 0, given that we found xy of t is equal to 0 and the expected value of x of t is n. So it's going to multiply out and become 0. Next, we're going to try and find out if it's orthogonal. And in order to do that, we have to prove that the expected value of x of t times y of t is equal to 0, which again, we already have done that up here. So it proves that yes, it is orthogonal.